Hello. We will start our session after 5 minutes, maybe. Till then, let everybody join first. By the time everybody joins, if you have any question, you can drop your question in the comment box or you can directly just ask. I think we can start our session. So I hope this video is being recorded. Hello, everybody. Good evening, all. Welcome to the week 3 lecture of doubt clearing session of Fundamentals of Additive Manufacturing. Hope I am audible to you, all of you. I think somebody can unmute and say, am I audible to you?
Yes, ma'am. Yes, ma'am.
Okay, okay. So, if you have any doubt, you can ask me. No doubt. If you do not have any doubt, then I can discuss all the topics that have been covered in this week briefly, or what you can suggest me. Anyone? No one? Okay, then I'll briefly discuss all the topics that have been covered in this week. So first is from starting from the last week's topics. In the last week, we have covered the slicing part. There in the lobby. We have covered the slicing thing. So how the slicing goes, like what all ways we can do the slicing. So there were that contour slicing. We can go for all the contours that are present in one object, and just summation of all the contours and trying to sort out the bigger contours which is present in the object and make the support structure according to that biggest periphery of the contour. But there the material lost is more, so therefore we went for optimal contour, where we just draw the contour of each slice, and then we try to figure out what all contours to consider for the support structure and what are contours not to consider for support structure. And then also I was trying to discuss the reason of using support structure, but that time my video went off, and then I created another link and made the rest of the video and uploaded it in YouTube. I don't know whether you guys have that link or not, but I think you'll be shared that link via NPTL. So then we know the reason of making the support structure in a part. And then from week 2, we got to know about direct slicing, indirect slicing, uniform slicing. Slicing can be adaptive, like finer layer thickness in the parts where there is intrinsic structure, or where we need more accuracy, or there is a curve or something different from a normal, very general structure. Then Then we had adaptive slicing, and then conformal slicing. So conformal slicing says that it needs higher than 3 degrees of freedom, where the build plate can tilt and rotate, and by which the material can get deposited wherever it needs. And the slicing can be other than planar. It's like angle slicing, where we can just minimize the use of support. So these times DED, directed energy deposition, has some robotic arm configuration where we can get this where we can use conformal slicing and get support free parts. Again, for lattice structure printing, support free part is very much needed, because in lattice structure, the unit cell of a lattice is something very crucial and something very intrinsic structure. So if we are having some lattices like this, and if we apply support structure in printing these lattices, then the accuracy of the lattice will not be that much what is needed. So conformal slicing is very much needed for printing lattice structures also. And these lattice structures are mostly used to have or to use their most desired benefit, which is the strength to weight ratio, which is very low, which is very high, because their weight is lowered down because of removing the volume, some density of material from it, and making structure which can bear more load. So high strength to weight ratio. Then we had that sorting of the triangles from STL file, and just select the slicing plane and see if this is the slicing plane and these are the triangles, then what all triangles are cutting the sliced path, and just by taking those triangles in consideration, we make the what should I call, the contour of the geometry, and by which we can generate the support, or we can make better slicing also. So these are mostly the overall topics that have been covered in the week 2 lectures. Week 3 mainly has considered one most important thing, which is the hatching. So I have to add everybody every time somebody is waiting in the lobby. Okay. So hatching means, okay, so can anybody tell me what is hatching? What is hatching? Anybody? This is supposed to be an interactive session. So if you have any doubt, you just ask me your doubt by unmuting yourself. If you do not have any doubt, you can just tell me what all questions I ask, so that you can have better depth and better understanding in this topic.
Ma'am, yet now I'm not completed week 3, ma'am. I completed only week 2.
Okay, okay, no problem. Anyone else who has completed week 3 and can tell me what is hatching? Nobody? Okay, no issue. Hatching means, till date we were talking about the slicing, the STL file formation. So if you can remember, then STL file is like, if I want to print this cube, then I'll make small triangles possible out of this cube to define the geometry or topology of the object to be printed. Now here I'm just defining the outer periphery of the object. But what about the inside? Inside, if I cut this cube, I have cut from this plane, and now this is the top view. So in top view, the print head can move like this to fill this cube if this is a solid cube. If this is a hollow cube, then the printing can go like, there is material deposited in the boundary and there is no material inside. Like, right? So this is called hatching, the infill or inner feeling of the printed part of printing. Okay, so hatching, now what is the big deal in hatching? Hatching defines everything about the part to be printing. Hatching defines the quality of printing, the property of printing. Property means I'm talking about the mechanical, metallographic properties. Okay, the accuracy, like quality means accuracy as well. Material, how much material to be used. In fact, hatching can vary the strength to weight ratio as well. And right back, I have discussed that what is a strength to weight ratio. Okay, why I am adding someone and she is not getting added anyway. Okay. So strength to weight ratio can also be varied by varying the hatching only. Okay. So in hatching also, the nozzle, if I talk about the FDM process, if anybody can tell me what is FDM process. FDM. That will be great. So anybody? Anybody? Who? What is FDM? What is the full form of FDM? FDM is fused deposition modeling. It comes under material extrusion. So in FDM, a wire is fed inside the nozzle. This is nozzle and this is feed wire, and this will get melted and deposited over the build plate. This is build plate. I hope you all remember what is build plate, over which the material gets deposited and part is printed. So the material comes and deposit like layer by layer. So this is FDM. In FDM, this hatch spacing and these things is very common these days. Like in FDM, we can get different lattice structures. We can print different lattice structures in hatch. So what I was talking about is tool path planning, which is the topic of this week's. Can anybody else join the attendees who are waiting in the lobby? Right now, nobody is waiting. Okay. So tool path planning. In the meantime, again, if you have any doubt, you can ask me. You can stop and you can ask me. Tool path planning means, so in FDM, the nozzle moves. So it is mounted over a CNC and wire is fed inside, and this moves in this direction, X and Y direction. Okay, and deposit the material, melted material, over the build plate. So if we are using FDM, then how this nozzle, how it will move to deposit the material. It's simple. It will move in X and Y direction and it will deposit, right? But what about the hatching? Hatching means the infill pattern of a material. So if this is the cross section of the material, which is a simple cube, then how the material will get printed? Infill, how the infill will be, like in this manner, or the infill will be in this manner, or infill is like one box apart, there is material getting deposited in one round, and then again the nozzle will come and deposit the rest of the white parts. Okay, so this is also called chessboard pattern. So how the hatching will be, how the infill will be, so that is how the tool or the nozzle will move. So the tool or the nozzle path planning is also important in any additive manufacturing process. Why there is sound but nobody is waiting in the lobby? I don't know what is happening. Okay, so then uh, this path planning is important. Tool path planning can be in three way. Tool will move to deposit the material in the outer boundary of the object. Then if there is any inner feature like if this box is having a hole inside, then it will print the material outside the hole, not inside the hole. And again, if this is a perfect circle, if this is a perfect circle, then it's also very important to get a perfect circle only, or geometry of a perfect circle inside the material. So again, there the slicing, the STL file formation, everything is needed so that we can get the perfect boundary of the circle. The circle should not look like this. The circle should look like this. Maybe this is also not a perfect circle, but yeah, somewhat like this. So inner boundary is also important. How the tool will move and deposit the material inside, so that internal features can also be accurately printed. And then lastly, the area filling. So this area filling is called the hatching. Okay, and these are the boundaries. Then next, so area filling can be in many way, like 2D filling. In 2D, you are just filling the area in different ways. Why I'm calling 2D? Because there should be a 3D also. So area filling. In area filling, that can be 2D or that can be 3D. In 2D, it can be like using grid cutting, and then pixels, mask, path, somewhat like this. And in 3D, it can be topology optimization. Means, again, you remember there was the conformal slicing where we deposit the material, in a 3D manner. Means the build plate can rotate or can get tilted into a particular axis, or the nozzle can just print the material. It can just tilt in certain angles and print the material. So in conformal slicing, we can get support free structure. So in conformal slicing, obviously, if the build plate is rotating and you're depositing the material, so the material deposition will be in 3D manner. For examples, in some portion the material is getting deposited, but in some portion the material is not getting deposited for a single layer. But in uniform slicing or other type of slicing, if there is one layer, then that in nth layer or in one layer, in all the region wherever the material needs to be deposited will get deposited. So that is 2D deposition. This is 3D deposition. In 3D deposition, we can make lattice structures in hatching. Okay, to make the strength to weight ratio more. So these are few techniques of area filling. So again, grid cutting, pixel, mask, path, these are different 2D slicing, 2D hatching or area filling techniques which are very popular. So there are many popular path planning or hatch strategies. These are not called hatch strategies, but there is something called hatch strategy. Okay, where we fill the area in different way. And what is this things like a snake? So it's basically the nozzle is moving and depositing material. So the nozzle will move like this, then this, then this. This is what I mean by this things. Okay, so the material can get deposited by this, like in a particular angle, or it can just deposit like this. Okay, This is called spiral. This again, okay, maybe this we can call zigzag. And if dotted line means at that portion the material is not depositing, only the nozzle is moving, coming back to the original position with turning off the material thing, material feed. This is called raster. So these are few hatch strategies using which you can feel the area inside it. Okay, so now if you have any doubt, you can ask me in between. Again and again, I'm saying. Okay, now there is one thing very important in this all type of raster or zigzag, or there is chessboard pattern also, I said. Then there is path, contour path, okay, contour parallel, then spiral, okay, then space filling. These are different types of hatch strategies. So in this all type of hatch strategies, the nozzle is moving in a particular manner, and it is getting, the material is getting deposited. For example, in raster, the material is getting deposited, then nozzle is coming back. Here no material, then again material deposited, nozzle is moving back, again material deposited. Okay, and in zigzag the thing is like material getting deposited, deposited. Okay, so what do you feel, what will be the difference between this one and two? What is the difference? Somebody please just unmute yourself and tell.
Ma'am, in dotted line, the material not deposit.
Yeah, so what will be the result, the difference in terms of result? What do you think? Any difference you think there should be?
Ma'am, raster, I
Okay.
think it takes
Yeah.
some more time. I think like it will nozzle will move up
Okay.
and down.
Hmm. Hmm. Yes. Yes.
In
Yes. Yeah. Yeah. Perfect. So yes, there will be more time in this raster. So apart from more time, it's like the nozzle is coming back, and at the time of coming back, there is no material. So basically, the nozzle is on here, then getting turned off, returning back, then on, then again off, then returning back. But here, if I correctly draw it, so it will be like this. It is actually looking like this. So here the nozzle is moving and there is no dotted line, means here also it is on, moving back, on means the material is coming, and off means the material is not coming. So here there is on off, so on and off both are present, means more time. This is one thing that you have said. The next thing is, I think there is someone waiting in the lobby. I don't know what is the issue with this. Okay, then if we are again turning on and turning off the nozzle multiple times, then one another thing is like, whenever you are turning off a moving substance, there will be an inertia. And when you are turning off, there is an inertia again at the last position. There is an inertia at the on position. There will be again one inertia in the off position. Again moving back, again one inertia here, one inertia here. So because of the inertia, there can be excess material dropping out from the nozzle or lesser material. Both can be the case. It depends how you are just turning off the material thing with the scanning. So in most of the cases, you are just normally going like, you are turning on the this is the path to be printed. You have turned on here, you have moved to here, and again at the particular point you have turned off. So basically here will be lesser material than usual, and here will be more material than usual will be printed. And because of which the accuracy will be disrupted. So this is again one thing, because of the inertia. Okay, so more time will be taken. Inertia is again a big problem. So there will be, if there is a very small part, and again you are moving, coming back, moving, coming back, moving, then because of the repetitive turning on and turning off of the nozzle, there will be vibration in the nozzle. Obviously the nozzle is attached to a CNC, moving, coming back. So because of which, because of the vibration, if there is any vibration, then that can again disrupt the part. But this amount is lesser because the CNC machine is should be a good quality machine, and again it should um, avoid the vibration also when the nozzle is coming, when and all those things, because there will be motor and leads go. But again, if there is lot of turned off and on in the whole printing, the vibration can be there. So these are few important points, those are to be noted in terms of the difference between raster and zigzag. So as a result, we can see zigzag is giving us better accuracy and better printing. Here the time will be lesser, obviously. Again, inertia problem is solved. There should not be any inertia because continuously the material is depositing and the nozzle is moving. There can be vibration at the time of nozzle movement, but again I have said that is not that much which can interrupt the part. So just leaving away the idea of vibration. So these are the main important points between raster and zigzag. Again, when you are printing, for example, a circle, okay, so you will print the path like, this is one layer, this is again next layer. There should not be any gap between layers. Okay, this is third layer, this is fourth layer, fifth layer, sixth. This is not number of layer. Again, I am saying something wrong. This is the nozzle, how the nozzle is moving basically. Okay, so nozzle movement start. This is 2D plane, this is XY plane, this is the area feeling I'm showing you. Something like this, the circle will try to get printed like. But if you see this periphery, then there will be this thing present. The circle will get printed like this. If this is not understandable, you can ask me. So because this is the nozzle, this, and by raster pattern, it is depositing the material. So obviously there will be humps, small humps in the periphery, and with layers, like this is the first layer where there is multiple tracks. These are called tracks. Okay. So multiple tracks are overlapped with each other. If this is one track, other track will not be like this. The other track will be like this. Second track overlapped. Again, this is one parameter that if this is one track, a zoomed view, okay, this one. The next track is like this. So how much is the overlap percentage? So again, we vary the overlap percentage at the time of printing also, means from the previous track, if this is 2 millimeter width, then next track will be starting from the middle of this 2 millimeter, and then again this is 2 millimeter. So now both the track will not form something like 4 millimeter, but again it will print something like total 3 millimeter. I think it is clear. So because of which the contour or the periphery of the printing is looking like this instead of this. Okay, which is not good. Again, this is not acceptable. Not acceptable. So what we do, we first deposit the material in the contour. Okay, so we can do the contour scanning. We will deposit the material like this, first contour, and then again second contour, then third contour. There will not be any gap in between, these are filled. Okay, and then it will deposit the tracks inside the contour. So as a result, the uh, outer periphery of the circle will be like this time. Okay, so which is acceptable. So this is a better way of depositing a material for a curved surface, because if this is a planar surface, if the periphery is like a straight line, you can deposit material anyway, because there no nothing will be there. But again, if this is a cube and you are depositing the tracks like this, then this part, this length will be like this, but this length will be like this again. So here also you can go with first contour, contour parallel scanning. This is also called contour path scanning or contour parallel. And then you do the raster pattern inside the part. So for the boundary, choose contour path or contour scanning. And then for inner filling, area filling, choose the zigzag or raster. In raster, there is movement, then there is back, then there is movement. So there can be just chances of making voids or pores, which is not good for a part. So again, zigzag is better than raster. Now there is one more thing which is called space filling, where the if this is a part, I'm trying to draw it, it's not very easy to draw. So the space filling path scanning type says something like, okay, the nozzle will move something like this. It's not exactly like this, but okay, so here the gap between lines are fixed. Somebody's waiting. Okay. And like this, the voids will be minimized. Okay, and it will be better feeling. Also, like this, the property can be to some isotropic. You're covering the part in a random feeling manner, so random feeling gives an isotropic property sometimes, because if you are directionally printing like this, every time the nozzle moving like this, then there will be a directionality in the part property. Directional printing, which gives an isotropic property. So here you are just minimizing that directionalism and randomizing the material deposition. So maybe to some limit the anisotropy can be avoided. And but again, there, when you move the nozzle like this, there is not any switch on off. If we are printing the part like this, there is no switch on off. But if we are printing something like this, so if I make, there is certain pattern present over this space filling. I don't know the exact pattern how to draw it, but I'm trying to draw something that you can understand what is the concept behind it. Okay, and out of this space filling, this space filling is also one example of Hilbert curve. Okay, and now out of this you want to make this pattern. So from this I'll take the space filling pattern, so it will look something like this. So there will be a lot of switch on off here. The switch on off has been increased now, because I have cut that proper Hilbert curve in the middle of it, because to cover my shape and geometry which I am desire to print. So because of which there will be a lot of switch off, which is again not good for our printing. We always try to avoid as many switch on off we can. So there this pattern is not good. Then comes something like median axis transformation, where you can print a job using some median axis. Think like, if this is a geometry and this is the median axis of it, like some axis which is covering the median of this particular geometry, and now you print material like in contour manner. Then there is one type of contour path. So basically, by using lines like contour lines, you are filling the whole area of the object. There again, the switch on off is more, so not good. And but the hatching is constant, so which is good. Okay. Uh, then this part is again good if you are having some uniform object like this. Okay, but not good every time because there will be lot of switch on off. Then comes our hybrid. In hybrid, so basically I have already shown the hybrid thing. This is the hybrid. So if we are making one circle, you first draw or fill the circle circumference with contour path, and then you go for area filling using zigzag or raster, so that you can minimize the number of switch on off needed for zigzag, is needed for raster. You can minimize the pores which are present in the periphery by using the contour. Again, you can get better accuracy in the outer contour. Someone is there in the lobby. You can minimize the or you can maximize the accuracy of the printing in terms of the outer periphery. You can make very smooth outer boundary or inner boundary as well. So if we are having one part, something like this, so you can just first do the contour scanning in the periphery. 2 layers or 3 layers of contour scanning you can do with constant overlapping tracks. And then for the inner filling also you can do the contour thing, so that you can just get a very smooth surface of the inner hole, and then you go for space filling. Okay, so this is called hybrid, means just mixing or combination of 2 3 type of hatching. These are some 2D scanning techniques or 2D hatch strategies that you can follow to print any particular geometry. Uh, in this also, these like what should I say? These 2D scannings are basically the hatch strategies, and hatch strategies are useful in case of material extrusion, then powder bed fusion, then directed energy deposition. Why I'm saying so? Because in 2D space filling, if you can remember, there was grid cutting. So this grid cutting is useful in case of, can you name which additive manufacturing use grid cutting? Any one of you who has watched the videos of week 3? No one? So any one of you who has watched the videos at least, so that I can have any idea that whoever has watched the videos and whoever not. No one? You can turn on your mic, or if anybody has watched the videos, they can raise their hand. That's more easy. I should reframe my question. Whoever has not watched the videos of week 3 can raise their hand. One. So the other guys are whether present or not. Are you listening, guys? Okay, second. B. Kiran, Shivahari, Thanga, Pandian, and you guys have watched the videos? Okay, not Mayank. Maybe they have. So, grid cutting is used for laminated object manufacturing, LOM. Okay. So, then we had pixel. These pixel things are mainly useful for the liquid additive manufacturing techniques. For example, the first one is VAT photopolymerization. Then we have, can you name whoever has not even watched the week 3 lectures but has watched the week 1 lectures? What are the liquid additive manufacturing techniques? Other liquid additive manufacturing techniques? Anybody? I just want you guys to interact so that I can understand whether I am understandable or not.
Rapid freezing,
Rapid freezing, anything else? I am asking from the
stylolithography.
seven. Okay, so I am asking from the 7 ASTM standard. Always try to read like that. That 7 classification under ASTM. Do you remember?
Ma'am, you asking that seven classification of additive manufacturing?
So I am asking that what are the liquid additive manufacturing techniques? But you name those techniques according to the ASTM standard.
Okay.
Like, for example, SLA, stereolithography. The ASTM standard calls it VAT photopolymerization, and under VAT photopolymerization, we have one technique called SLA or rapid freezing, another technique. So, like that, if you can remember any other liquid, or I can tell you the names, you can just say that this one is liquid. First one is VAT photopolymerization. Is it a liquid technique?
Yes, ma'am. It's liquid technique and least energy consuming method.
Yes, yes, good. The next one is material extrusion. Is it a liquid technique?
I think it's wire.
It's wire. Yes, I have already discussed FDM. Then it's we have material jetting.
Yeah, ma'am. Jetting it's use liquid.
Liquid. Okay. Then we have binder jetting.
Binder jet also using liquid.
Okay. And then we have binder jetting. Actually, not liquid, but it's like mixture of liquid and solid, because the binder is coming that can be liquid, but the raw material is in powder form. So yeah, you can count it as liquid, but I would not suggest it you to count it as liquid. Anyway, that is not again so much popular technique. The next one is sheet lamination. Okay, it's
Yeah,
not liquid.
here
It's
using
it's
sheets layers.
yeah. The name itself suggests the sheet is a raw material. Then we have powder bed fusion.
We are here using we
Again, the name suggests
solid solid particles.
powder. Yes, solid particle, solid powder of metal or polymers. And then we have directed energy deposition. It's not. Okay, so DD is not a liquid process again. DD also uses wire or powder form of metals, no polymer. So, liquid techniques we have VAT photopolymerization and then material jetting. Binder jetting also, but I'm not writing that. That is not that popular. So, this things uses pixel. Then we have mask. Again, VAT photopolymerization. So VAT photopolymerization also having lot of more techniques like top down approach, bottom down approach. So SLA, DLP, LCD based printing, rapid freezing. These all are VAT photopolymerization technique. So different VAT photopolymerization technique has different aspects. So Vivek has raised his hand. He can ask me the question he's having.
அழுகாதீங்கடி.
Do you have any question, Vivek? No. Okay. If you have any question, you can post it in the comment section. Then mask is also useful for photopolymerization. It is. Then mask is useful for loam also sometimes. Then we have path. So path is useful for every type of additive manufacturing processes. All M path can be used. So what is grid cutting? So if we are having sheet lamination process, this is the paper sheet and I want to print one object like this. So the laser will come and it will cut the object in this manner and the rest of the sheet will just move on to the bin. Okay, and we now have this object. Again, another sheet will come and laser again will cut the object like this and it will overlap, it will fall over this sheet exactly, and all the thing will get glued to each other with a little bit of heat and roller pressing. So here, grid by grid. So if we just just make grids over this whole paper by the machine, so the laser head will move by this grid calculation, grid by grid, and it will cut the unwanted part. So in every type of additive manufacturing process, we deal with the wanted, like we deal with the material or we deposit the material, we deposit the binder, or we use the laser consolidation only where the object needs to be printed. But loam is the only process where we use the laser, the energy source, to cut the material where it's not needed. The material which is not needed, it just cuts down. So this is the only process, only unique process. So always remember. Then this is the grid cutting. Then again, if you talk about pixels, then we have VAT photopolymerization. I'll come to that topic later. But before that, we have mask, which is again useful for VAT photopolymerization. I'll come to that later. Path is like we have discussed already the different hack strategies. So depending upon that, the tool will move, deposit the material, or in powder bed fusion, powder is spread over the bed. The laser moves and consolidate or melt the powder particles present over the powder bed wherever it is needed, wherever the object needs to be deposited, object needs to be met. So this is the basic difference between different additive manufacturing processes. Now, after this topic, one software was demonstrated in week 3 lectures. So I cannot demonstrate the software right now here, because I don't have that software. You can use that for tool path planning. It's very easy software. It says that how you can just that Inkscape. Inkscape software is useful for this tool path planning, how the tool will move. So this software is basically useful for CNC cutting, because in CNC cutting you have a sheet, or you have a block, and the CNC head will come in the head. Different types of tool can be attached, like drilling tool or milling tool or cutting tool, and that will just move over the object and it will cut the material, and it will make beautiful geometries over the sheet or block. So the tool needs to be moved. So Inkscape software is used to plan the tool movement. So basically, it generates the G code and M code. If you have very general design, you can make your own G code M code just in writing in pen and paper. And if you're having something very complex, you use the Inkscape. So here we can use the Inkscape to add the material. Like Inkscape doesn't understand whether he's cutting the material or removing the material or depositing the material. It just understands the how the tool will move. So there in CNC the tool moves to cut the material. Here CNC moves to add the material. So Inkscape can be used to plan the tool path. So there is a beautiful uh, example shown in the lecture video of professor. You can see where you can convert a 2D picture into a 3D sketch in Inkscape and define the tool path planning in such a way that the material will deposit over the picture in such a way that a sketching of the picture can be printed like few layers over the build plate. So that is one thing. It's very easy again. But if you are having a printer, you'll have its own licensed software. If you're not having, this sort of softwares are useful to make the tool path. And again, for slicing, you need different software, because after the tool path, you have to slice the parts. Or planning can also accommodate the slicing as well. So both the things are different, but you can try out this new software. The next thing, which is like up to here, this was week three's lecture one. Inkscape was demonstrated in lecture 2. You can really download the software and do something in the software. And if you feel any difficult, you can just post your question in the Q&A session. Then I'll download the software and see what are the things. And from lecture 3, the liquid additive manufacturing processes were demonstrated. Liquid aim process, such as one is wet photopolymerization. The next is sorry. Next is binder jetting as well, but these two are the most important thing. So here we use the pixel or mask things mostly. Pixel thing can never be used in any solid additive manufacturing process, and mask thing also can never be used in a solid additive manufacturing process. So these two are mainly useful for the liquid thing. And again, for VAT photopolymerization, you can never achieve any path planning like hatch strategies, what I have demonstrated, the zigzag pattern or raster pattern or spiral, space filling, Hilbert, these things can never be used in vat photopolymerization because it's a liquid raw material. So material cannot come from the nozzle. Although in material jetting the liquid comes from the nozzle, but it can never get deposited using those patterns, especially in vat photopolymerization where we store the liquid material in a vat or container. This rastering or hatching strategies can never be used. So we have to have some very special space filling technique for this type of liquid aim process. So can anybody just tell me what is vat photopolymerization and how it works? Because I have already discussed it in my first lecture. So anybody? I think you guys know. You can tell me. No one? You guys can unmute yourself and tell me what is
Ma'am,
vat photopolymer. Yes,
ma'am, I was
please.
absent, ma'am, in first lecture.
Okay, you were absent. Anyone else who knows what is vat photopolymerization?
Yeah, photopolymer is cured with the help of light.
Yeah, photo curable liquid material gets cured with the help of light. So we have taken few important points about vat photopolymerization. One is photocurable material. Next is cured, and third is under the exposure of light. Photocurable material means resin. We use different types of resins. So again, resin is a kind of thermosetting polymer. Anybody can remember what was thermosetting polymer and what is thermoplastic polymer? Any guess? For example,
Thermoplastic
FDM uses.
recyclable.
Sorry, can you
Reusable.
repeat?
Yeah, thermoset.
Any guess? Hello?
Which can be melted and reused.
Which one?
Thermosetting.
Thermoplastic or thermoset? And
Thermoplastics.
thermoplastic?
Yes.
Okay, and thermosetting?
Thermosetting cannot be recycled,
Yes. So
reused.
thermoplastics can be melted, solidified, again remelted and reused, but thermosetting, once it is solidified, it cannot be remelted. It will be burnt if you just expose it to high energy light again. So we use resin, which is a it's thermosetting polymer. So different, I said different types of resins are used. So can you tell me what is different types of resins? What do you mean by different types of resins?
Ma'am, can you repeat once?
Yeah, I said that for wet photopolymerization, the material, the raw material is photocurable material. For example, resin. And I said different types of resins are used. So can you tell me what do you mean by different types of resins? How do you differentiate between different resins? Hint is it is photocurable. No guess. Any random guess? No guess. Okay. So the hint was photocurable. What do you mean by photocurable? Anyone? Any
Yeah,
idea? Just
if the,
as the name
yeah,
suggests.
if the light falls over the resin, the monomer
Yeah.
will convert it to polymer.
Okay. Yeah. So if we expose the liquid resin to a particular light,
Yes.
the resin will get solidified. So
Solidified.
different
Yes.
types of, yes. Did you say something? I missed.
No, no.
Okay. So photocurable resins and then different types of resins means that you will find resins who get solidified under a particular light. Now, what do you mean by particular light? Light has a specific wavelength. So, like the visible light is having the wavelength range from 400 to 700. So, it's a huge range. But when you use red light, you have some wavelength around 350. When you have blue light, you have wavelength range around 450. When you have green light, you have wavelength range around 530. So like this, you have different types of uh, wavelengths. Okay, I said some mistake. So ultraviolet rays are having lower wavelength. So violet light is having some wavelength range around 350, and red lights have wavelength range, I think, around 600 or 700. Okay, and after that the infrared starts from 800 and goes till like forever. So these are some lights. So these lights are monochromatic lights, and monochromatic lights means there will be only one wavelength present, and the resins have a specific characteristics, like if you solidify the resin under the sunlight, it will not get solidified. But if you expose the resin under a particular wavelength light, then only it will get solidified. So different types of resins means resins get solidified under particular wavelength. Lambda is wavelength. Okay. So you can find a resin which is 350 nanometer curable. One is 450 nanometer curable. One is 294 nanometer curable. So you have to expose that resin under that particular UV ray or light only. So if you are having UV light, Then again, UV light is a light source which is having again broad wavelength spectrum, but the spectrum starts from 350 and below. And if you are using laser light source, because here the third important point was light. Light means it can be UV light or it can be laser light. For laser also, we use lower wavelength lasers like violet laser, blue laser, and UV light is again having a spectrum in ultraviolet range. And the second most important point was cured. Curing means solidified. Cured means solidified. So curing means solidification of resin under the exposure of light. Okay. So these are the three main aspects related to the wet photopolymerization technique. You have to have a liquid resin. You put it in a vat. Vat is a container where we pour the resin. Resin is the raw material for wet photopolymerization. The liquid resin is cured, and if you have a bill plate, you can print the part on that bill plate. Now, I was talking about the tool path planning. So, uh, mask and pixels are the most important thing in wet photopolymerization. So, what we do, the first approach is called top down. Okay, so you have a bill plate. From here, the liquid comes. From here, the laser comes, and this liquid head moves in XY direction. So it will just solidify it. The resin which is spread over the bill plate by the exposure of light. Laser is also a light source. Okay, do you know the full form of laser? Anyone? Any guesses? Okay, laser is light amplification by stimulated emission of radiation. So laser is also a type of light. So if light is being exposed, so the resin will get solidified. The second technique is again top down approach. So where this bill plate will be dipped under a vat in such a manner that the resin is present in all over the vat, but the build plate is dipped down in such a manner that over the build plate only one layer of liquid resin is present. Now from the overhead, the laser or UV light is coming. So if it's coming and interacting with the material present over here, it will solidify or cure the material, and the material will get solidified. When first layer is done, this is first layer. So the bill plate will lower down by again one layer. Now over the bill plate there is one solidified layer and one liquid layer. This is liquid layer and this is solidified layer. And again the full of resin vat is present and the laser is again coming from the top. And this is how until nth layer the bill plate will keep moving down by each layer thickness with each layer, and you will have the whole material printed below the vat. Again, this is the liquid layer and this is the solid layer. So this is how top down approach works. Now we have bottom down approach, bottom up approach. Okay. So in bottom up approach, we have again a vat full of resin. The bill plate is attached to a long column and it is dipped down inside the vat. it will start the exposure from the bottom of the vat, not the. Okay, so here in this approach, first the first layer was solidified, which was bottommost layer, and then in the nth layer, the last layer is solidified. So there is no difference in these technique here. Here also first the bottommost layer will be solidified, and in nth layer, which is the last layer, the uppermost part layer will be solidified. Okay, only the bill plate is vertically upside down. Okay, so this bill plate will be dipped inside this vat in such a manner that inside, in between this bill plate and the vat, there will be only one layer of resin is present. Okay, now the laser will the UV light will come from the bottom part. It will solidify the layer wherever it is needed, like in all over the bill plate. You may not print the part, you may print the part at the middle, or you have 4 or 5 parts spread over the bill plate. So wherever it is needed, the UV light will solidify at that position only. So this is the whole picture of different techniques of vat photopolymerization. Okay, remember this process, flow of this process. But how you are curing each layer, that is again important, and that is very much different from other aim processes. Like first I said the curing. So let me first explain what is curing. So polymer is made of small millions of monomer. Polymer is made of lot of monomer. Monomer is a single unit of polymer. So if this is a monomer present inside the liquid resin, along with this monomer, as resin is a photocurable polymer, so there will be some photoinitiator present inside the liquid resin. These bigger chunks are the monomer, and the smaller chunks are the photoinitiator. Always remember, photo means light here. If you know photosynthesis, trees are doing photosynthesis to make their own food. There also photo means light. They're using light to make food. Here also photopolymerization means polymerization reaction by which monomers get attached to each other, make long chains and make polymer, is initiated by photo means light. Photo initiators, what they do, so when the resin is exposed to some UV light, if UV light is falling over this set of monomer and photo initiator, the photo initiators, what should I call, they release some free electrons, and these free electrons vibrate uh, because of the absorption of light inside it, and because of that they make long chain between monomers, and thus they get attached to each other, and then they make the whole bond of polymers. Okay, so this is the process physics of curing process. Curing is a process by which the photo curable polymers get solidified. So I think this is again understood. So in vat photopolymerization, there is three things. One is material aspect, I have discussed. Second thing is curing, I have discussed. Third thing is light, which I have also discussed. But what I haven't discussed till now is the tool path planning of vat photopolymerization. So again, I said in tool path planning here, pixel and grid and mask is used. So how it is used? So for one example, there is one VAT photopolymerization technique which is called LCD based DLP technique. DLP is digital light processing, DLP, and there is one process called LCD based DLP. LCD means the normal NCD, which is liquid crystal display. So what it does is there will be a LCD screen placed below the VAT. I should draw a straight line. So this is a LCD screen. Okay. And this is the VAT full of resin. So can anybody tell me if this is a bottom down approach, then how the bill plate will be present inside this VAT? Anybody? Just now I have discussed.
Bottom to top approach, ma'am.
Yeah, so the bill plate will be, the correct answer is the bill plate will be attached at the bottom part of the VAT.
Yes.
It will be present at the bottom part of the in the inside the VAT, and it will go up with each layer, layer by layer basically. So what happens is from the below portion the UV light comes. So if the UV light is coming from the bottom, it should reach all the liquid present over the first layer of the bill plate, in the bill plate, right? But it doesn't reach in the whole bill plate. If it reaches the whole bill plate, then all the resin which is present in the bill plate will get solidified. Then how we can obtain a particular geometry or topology? So what happens is there is LCD screen. In LCD screen, there will be small square pixels, the pixels which are present in our camera, in our phone picture. So when you take a picture and if you zoom it, sometimes we see the picture gets divided into pixels, and we say the picture quality is not good, right? So that is how here also pixels work. So LCD screen is consist of small pixels. Okay, consider this a perfect pixel photo. So this is one pixel, and in the LCD screen, for example, lakhs or millions of pixels are present. Now if I want to make a geometry like this, so this is the geometry. Okay, so from the bottommost part of the LCD, the UV light is coming, and in this part the liquid resin is present. So what will happen, the pixels present in this part of the object will get activated, and from that part only the UV light will reach the substrate where the liquid resin is present. And thus only at this part, this is a doll, and at this part only the resin will get solidified. In no other portion the resin will get solidified, and with each layer only there the pixel will get activated where it is needed, and from that activated pixel parts only the UV light will reach the substrate. And this is how pixels work. Now you imagine, if you have a very good phone, like for example, in our daily life, when we take a photo in Oppo or Vivo, if we zoom the photo, we see that the picture is getting divided in pixels, and the quality is degrading, so it's not a high quality camera. But when we take photo in iPhones, however you zoom the photo, you'll never see any pixel distribution in the photo. So because the image processing, the pixels are very small. Like even if you zoom by 5% or 5x, you cannot see the photo divided into pixels. So that is how it also works. If in LCD screen there are millions of, or there are billions of pixels, the image quality will be better. Like the part quality will be better. There will be no sharp edge or distinct periphery in the object, which is like showing the pixels. But if the number of pixels are lesser, then the image, the part quality will be bad. So if we are having this geometry, and if you are having very fine pixels, so basically you cannot see the outer, like you'll get the object finish like this at the end. But if you are having very low quality pixels, like bigger pixels, then you'll get the object quality like this at the end. This is low quality, obviously, and this is high quality object, because here the number of pixels were high, and here the number of pixels was low. So this is how the pixels work. The next thing is mask. Again, mask is like, there is a glass. So when the light comes like this, it can fall over a scanner. This is a scanner. Okay, scanner means mirror, which reflects back the light. So if this is reflecting back the light like this, the light is falling over something. Okay. So same way, if we are using again the bottom up approach, the build plate is here, and now at you're not using any LCD screen. What you are using is, from this part the UV light is coming, and here a galvo scanner is present, which is projecting the light in this photo. Okay. Now in galvo scanner, there are small grids present over there. Not grids, there are small mirrors present over there. Okay. And if this is a galvo scanner, you can see the lecture, the professor is showing one galvo scanner, where you can imagine how the galvo scanner looks like. So there will be mirrors, small mirrors present in the galvo scanner. When the light is falling over these mirrors, this mirror can get tilted. Okay, they can, like, this is the first position, they can move like this, or they can move like this. So they can just tilt a little bit. Okay, they can move in their own axis, so that they can reflect the light and project it onto the substrate. So only those mirrors will move and project the light on substrate where the object needs to be solidified. So all the mirrors will not reflect the object in the build plate. So basically they will make a projection of light in the build plate, which is called the mask. And using this projection on the projected area, the resin will get solidified. So this is the concept of projected light DLP, and LCD based DLP comes under wet photopolymerization. So if you have any doubt in this topic, you can ask me. This projected light thing and LCD based thing, because this is a bit complicated, because I don't have any photo or video of those things. No doubt? Okay, good. So there is one thing in this galvo scanner. So galvo scanner is a very important equipment in additive manufacturing technique. Not only in these VAT photopolymerization, but also in other additive manufacturing technique, this galvo scanner is used. Why? So we can use a normal scanner. Scanner means just a mirror. So the a mirror, okay, which is having anti-reflection coating behind it. So this surface will reflect the light, but the back surface will not reflect the light. Okay. Because if the light is falling over this and it is reflecting back, and if this is a transparent mirror, all the light will transmit in this transparent mirror, and no light will come in this spot, because this is the build plate. So the light which is coming here should be reflected back and go to the build plate fully. No loss will be there. No loss should be there. So this is why there is an anti-reflection coating behind the mirrors. So we can use any scanner like this, any mirror like this in our study, and the mirror will move and project the light in all over the build plate. Why you are using galvo scanner? Because if you want to project the light with good accuracy, you need multiple mirrors. Obviously one mirror cannot project the uh, image of the object over the build plate, or cannot project the light in such a manner that an image of the object will be made over the build plate, and in that particular image area only the resin will get cured. So we need to use multiple mirrors. Now if we are talking about multiple mirrors, then I'll just attach multiple mirrors to a CNC head, and I'll command the CNC like using G code and M code, like you should move this mirrors at this position for this layer, and I'll give command to the CNC like you should tilt these mirrors like A B C D E F, only these four mirrors in 45 degree to project the light over the substrate for the n plus 1 layer. Not any issue. But the galvo scanner has the advantage of moving or tilting the mirrors in a very high speed, very high speed. So what will happen if you are using CNC at that place? CNC uses some motors, lead screw connections. So CNC cannot give you that much high accuracy in that rapid movement. CNC cannot give that rapid movement, but galvo scanner can give. So that is why in various additive manufacturing techniques like in LPBF, galvo scanner is a must. In DD also these days people are using galvo scanner in few cases just to project the laser light over the build plate. So galvo scanner is used to move the laser beam over the build plate with a fast speed, like very rapidly, which a CNC cannot do. So you can write down this point, like the main advantage of using galvo scanner is galvo scanner can move the laser beam very rapidly. And other thing is the CNC can also move the laser beam with fast speed, like very rapidly. But if CNC is moving, there will be vibration associated with the CNC head. But galvo scanner is a optical series of mirrors, so it doesn't vibrate that much when it moves the mirror. Okay, because these are lightweight small mirrors. So galvo scanner, this is why is very useful in AM processes, especially in this wet photopolymerization technique, powder bed fusion technique, which can give very high accuracy in moving the laser beam or moving the UV light over the build plate. So these are few things, few important things about the tool path planning of wet photopolymerization using galvo scanner. Then in tool path there is mask and there is pixels. So mask is basically if the whole UV light is supposed to come in the build plate, but I want to make this geometry over the build plate, so I am just making a guard in the rest of the portion of the build plate and letting the light pass and come to this desired position only. So this is what mask means. That is why it's called mask. So pixel and mask. And then for wet photopolymerization, there are three main topics. What is photocurable material? Resin gets solidified at particular wavelengths only. The second thing is curing, like the monomers get uh, the electrons emitted from the photoinitiator because of the exposure of a light, particular light with particular wavelength. And also remember, the resins are photocurable at particular wavelength. So that means if you are having a liquid resin and that resin is 350 nanometer photocurable, then the photoinitiator will release the electron or will vibrate and get excited and release the electron only if you are exposing the resin at or with 350 nanometer UV light only. So this is the meaning of particular wavelength photocurable resin. So then the photoinitiator will just tag all the monomers and they will get connected to each other. They will make long chain, and that is what a polymer means. So this is how they get solidified. Uh, they comes to each other very closely and get connected or linked together. Then light means UV light or laser light we can use. If UV light, then again you should use a particular wavelength UV light because resin will solidify it only if you are exposing it to a particular wavelength. And laser light, blue, green, these are some lower wavelength lasers which are generally used in this wet photopolymerization technique. Then again, we have SLA. In SLA, laser is used, stereolithography. In DLP, laser, and mostly in DLP, UV light is used. It is digital light processing. And then there is rapid freezing, which has not been discussed yet. And in SLA or DLP, or particularly in wet photopolymerization, there can be this spreading technique, like the liquid will be spread. There can be top down approach, there can be bottom up approach. In every approach, the material will get deposited from bottommost layer to the topmost layer. Only the thing is, in bottom up, the part will be printed in the upside down manner. And this is the curing technique. Also, one important point is, in wet photopolymerization technique, the whole layer gets solidified in one go. So time taken is less. If you wanted to print a geometry like this in wet photopolymerization and in FDM process, which is material extrusion, always wet photopolymerization technique will take lesser time than FDM. Because in FDM, the nozzle will move and deposit the material. The nozzle will move like this and deposit the material. Okay, but in VAPP, the light is getting exposed to the whole layer at the same time. All the pixels are getting generated, or using the mask, the whole light is getting projected on the whole layer. So the layer is getting solidified in one go. There is no pixel to pixel solidification. Okay. So this is why this takes lesser time. Also, one very important point is the support structure. This is very important that when you deposit material in wet photopolymerization, you can never get a quality like you get in a liquid AM process. Like material jetting at wet photopolymerization gives us the best quality product in all other AM processes. But unfortunately, they are only able to make polymer parts, not metal. But for polymer also, these are the best techniques in terms of accuracy, like near net shape manufacturing or full density part. They can make a full density part in just one go and with lesser time. Also, support structure is not needed in every single part printing. Like in wet photopolymerization, you can print easily the lattice structures without any support, because the pixels are getting activated in one go. So in one go you can cure a full layer. So that's why no such support is generally needed. But again, if there is a lot of overhanging portion, then only you need a support. But the tolerance here is much higher. Then yeah, so these are some important points in these wet photopolymerization technique. One more topic that was covered in last class, which I missed, is only two topics are left. So in between, again, if you have any doubt, you can ask me. Somebody's waiting in the lobby. So if you have any doubt, you can ask me. Do you have any doubt? Anyone? Any doubt in
No doubt,
all
no
the
doubts, ma'am.
no? Okay, okay, okay. So only few minutes are left. So I'll quickly cover the left over topics. So one thing is hatch strategy. So again, hatch strategy is not needed in vat photopolymerization. So I'm talking about the solid AM process. In hatch strategy, we basically plan the tool path inside the material. Okay, so there is one thing called the lattice structure. So I can't show you any lattice structure right now because I need a photo. I cannot draw it. But it's like you can print lesser density part in solid AM processes by incorporating lattice structures inside the area filling. So instead of feeling, this is the cross section. Instead of feeling the part like this, tracks overlapped with each other, you can print it like this. So it's basically a lattice structure, okay? And each time I'm moving my pen, don't consider that these are one line. These can be multiple lines, means one in this one line there are overlaps of tracks. So this is how you can minimize the density of the whole part. Why it is needed? Because sometimes to reduce the weight of the part, reduce the weight, increase the strength to weight ratio, because uh, lattices are having more strength and lesser weight. So you can effectively reduce the cost. But again, for lattice printing, if it's not that complicated, then you can reduce the time as well. Okay, so these are few things about the solid AM process, that you can reduce the density of a particular part if you are printing one block and you don't need the full density part, then you can incorporate any hatch strategy in such a way that you'll make a lattice and you'll reduce the weight without hampering the strength. And the last topic which is left is like, for any AM technique there are four things. One is the material delivery system. The second thing is heat source. The third thing is manipulator. And the fourth thing is like the part printing, like the bill plate attachment. Okay, so in VAT photopolymerization, the bill plate moves in Z plus and minus, not nothing more than that. Manipulator, like the bill plate is attached to a lead screw, and the bill plate simply moves in Z and Z plus and minus, so nothing complicated. As a heat source, we can use UV light or laser, and the heat delivery system is also important. So, like heat delivery system, you can also say in VAT photopolymerization, the heat delivery can be using galvo scanner or can incorporate the LCD based DLP, or just can be the simple exposure of UV or laser from the up, like the spread in the spreading configuration or in the top down approach. And material delivery is, here we do not deliver the material from here and there, we just store it in a particular vat, or you can spread the material as I have shown in the first configuration. So spreading is not that much popular these days. It is kind of almost obsolete. Before it was there, but right now there we only use vat of liquid. So material delivery is not that much complicated here. In some cases we use recoater to coat the first layer of material over the bill plate, then the heat source come, for example in powder bed fusion. But here we just store the liquid in vat. So there are few important aspects in a additive manufacturing technique. So just changing this material delivery, heat source, manipulator, and heat delivery system, we can change the whole process of aim. So under VAT photopolymerization, we are having DLP, digital light processing. We are having SLA, stereolithography. We are having LCD based VAT photopolymerization. We are having the projected light DLP. So in all these cases, now you'll see whether the heat delivery system is different, or the manipulator is different, or the heat source is different, or the material delivery is different, or the bill plate which is uh, connected to the manipulator is different. Like it can have more than Z plus minus movement, like it can have XY movement also. So these are the differences we have in aim processes, and depending upon which we do have the classification of 7am technique. But under 7am technique also there are multiple methods. So depending upon these four configure depending upon these four um what should I say aspects, we get different aim processes. This is all about the week 3 lecture topics that has been covered. Okay, so yeah, the solution to assignment 1 2 needed. Okay, if you are talking about the solution of the week 3 quiz, then I would say that week 3 quiz timeline is not yet done. So week 3 quiz, related to week 3, if you are having any doubt, we can solve it in the next class. But if you are having quiz related problem from week 2, then we can solve right now. If you have any doubt till now, you can ask me. Or okay, the page is also done. So these are my email ID. You can just mail me also your doubt, or you can just post your doubt in the Q&A section of the Fundamentals of Additive Manufacturing, right? Or you can post it in the next class also. That will be solved. Okay. So I think you don't have any doubt. If you have, you can ask me.
Ma'am, what is difference between FDM and 3D printing?
FDM and which printing?
3D printing.
Okay, 3D printing means additive manufacturing. Okay, whatever we have discussed till today is they are type of 3D printing techniques. Okay, and FDM is one type of 3D printing. So as I have said, according to ASTM, we have 7 different types of additive manufacturing, and additive manufacturing is also known as 3D printing because we are depositing the material in layer by layer manner and we are making a 3D object. That's why it's called 3D printing. And in 3D printing, there is one type of 3D printing which is material extrusion, and where there is one method called FDM, fused deposition modeling. So it's a type of 3D printing. It's not different from 3D printing.
Okay, thank you.
Maybe with lectures, the 7 different types of 3D printing techniques will be discussed in subsequent lectures. So I can discuss them all in the subsequent doubt clearing sessions. So along with that, if you have any other query, you can post your doubts in comment section. You can post your doubts in my mail, or you can post your doubt in the Q&A section. Okay. And you can also try to play with the software Inkscape. It's a really good software. I have seen it in the lecture video, but I haven't downloaded it yet because I have software related to every machine I use for my PhD, so I really don't need any additional software. So yeah, that's about it.
Thank you, ma'am.
Okay, then thank you. Thank you and good night.